Okay. We're going to talk a little bit about graphing these polar equations, or we can think of these as kind of polar functions, where r is written as a function of theta. Okay, so here's how I'm going to kind of try to help you understand this. Here's our polar graph. Okay, so the way that I think of this is on a xy coordinate system. It's like for every x, you're plotting what the y would be, either below or above that x, and you're getting these graphs. So y is a function of the x. Well, here, r is a function of the theta. So what I created here is like a little print arm that extends. I tried to make this so it would extend back and forth. Do you see how it goes back and forth like this? I was trying to be clever, I guess. And so the idea is, as this thing spins around, it prints, okay? And then where it prints is a function of theta. So whatever angle it is, it's going to print at that angle, okay? So think of this as being kind of a print head going around, going in and out. And wherever it prints for any given angle is determined by this equation here, okay? And so one thing you could do, I'm not going to take a whole lot of time to do this or whatever, is you could put different angles. Like I could put 0, pi over 6, pi over 3. Where's my pen? You could put like 0, pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, whatever it is. And then this would be, you would have your function, you would plug in this angle, you would calculate r, and you could write r down for each of these. So for each of these angles, you'd be putting a point wherever the r was, whatever the formula gave you for r, okay, and then it would trace out the graph. So we're going to do this by I'm going to just show you on this calculator, and then you can play around with this on Desmos. Now, what I'm going to do is I'm going to try to find a good video on YouTube that talks about some of these cool graphs that you can do. But for here, I just want to show you on here. So when you hit mode, there's several different types of graphing modes here. You can graph a function, and up to this point, that's probably all that you've done. There's parametric equations. Maybe you've done that if you've had it in physics or something, or a high school calculus class maybe. And then there's polar coordinates, which is what we're doing now, and then sequences, which is something that you don't do until you get to Calc 2. So we're going to learn how to do function, parametric, and polar. So one neat thing about this class is you learn about 3 out of the 4 type of graphing utilities on here. So I'm going to go over to polar, and I'm going to hit return. And now when I hit my Y editor, you see what I have here is R. Instead of y equals, it's r is equal. Okay? So if I did like r is equal to, let's say, r is equal to 4, or let's say r is equal to 5, this is going to be a concentric circle. This is the constant for a polar graph. It's where as you spin around, the r is always equal to 5. So in other words, here's my print head. And the angle doesn't matter, the r stays the same, and it just prints out a circle. Okay? That would be the idea. So now if I hit my window, you can see that there's several things to set here. Okay? There's, first you're setting for theta. So I got my theta min, theta max, and my step. Okay? So basically, the theta min is the lowest theta value. It's gonna start by evaluating theta there and getting r's, and then this will be the maximum one. Okay, so you're going to go from theta from 0 to, you could do 0 to pi or something, or 0 to 2 pi. So the default, I think, is 0 to 2 pi, and that's what it's set at now. So the step is how big it is. It's going to evaluate it, like if I did it for every pi over 6, pi divided by 6, it would look like my, sorry. Let me do this again. This is 2 pi. So if I did pi divided by 6, my step would be 0.5, almost a little more than 0.5. So what they probably have there, I'm thinking, is what they had initially, the 1.3. I don't know. Is it pi divided by 12? No, but it's pi divided by 24, I think. Pi divided by 24. Yeah. So what they're doing is they're going every pi divided by 24, which is like 7.5 degrees. Pi divided by 6 is 30. Pi divided by 12 is 15. And then pi divided by 24 is 7.5 degrees. So they're going to evaluate it, or they're going to do a little print for each one of those, okay, around the circle, okay, for each of those angles. So this is my window. So I'm going to go from, this should be the pi divided by 24. And now this should be my x min. I'll do -10. My x max is 10. So the window here is setting your actual like rectangular coordinates for the size of the window that you're going to look at. Okay? And now I can hit graph, and you see that it actually traces that out. Now that does not look like a circle, but it's because these scales are not the same. So I can hit zoom and do zoom squared, and now it looks more like a circle. Okay? So now the interesting thing then is if I go from 0 to pi, can you guess what it's going to trace out? Instead of going from 0 to pi over 2, it just goes from 0 to pi. And so what it traces out is half of the circle, right? So that it matters here. So it matters what that theta range is, the interval that you do for theta. So I could do 0 to 3 pi over 2. And if I do that, then it goes 3/4 the way around the circle. Okay? And so that's how that works. That's how you set the range here. So now let's do something else here. Let me go to here, and I'm going to get rid of that. And let's say I do, we'll say 5 cosine theta. And I want to do the whole, actually I'm going to do, I think you can do this just through, all you need to do is 0 to pi, and it'll trace out the whole circle. Okay, so if I go to graph, okay, so that's the circle here that has a radius or a diameter of 5. So let me do one with a diameter of 10. Oops, that's a diameter of 100. Quit. Sorry, a diameter of 10, and then I'll do cosine theta. Okay. Okay, so this window is like 16 by 10 or something like that to make it square. And so these are the circles here that are, like I was saying before, this is to the left because the 10 is positive and it's a cosine. So if I go back here and I do cosine, or if I do sine, then it'll be a circle up above with a radius of 10. Okay, but then if I do shift, insert, and I make it a negative, then that'll put the circle below. And then if I go here and I make that a cosine, then that'll be a circle to the left. Okay? And notice for this circle, you don't actually need to go from 0 to 2 pi. If I go to my window, I'm only going from 0 to pi. See that? And so if I actually go to 2 pi, you wouldn't know it, but this actually ends up tracing the circle twice when you go from 0 to 2 pi. Okay, you just need to go from 0 to pi, and then you'll trace it once. But if I go from 0 to pi over 2, can you guess what's going to happen? It gets half of the circle. Okay. And then if I make that positive, then it'll be that half of the circle. Okay. So so I wonder if I did this, and I went and I did a negative 10 cosine theta, and did both of these, then I'd get that. I did the bottom half and the top half, and I guess it did it 2 different colors, didn't it? So those are some things that you can do. Now let me show you a neat curve that's not terribly difficult. So I'll do 5, and then in for cosine, I will put, I don't know, we'll do 5 cosine 4 theta. So I'm putting a 4 inside my cosine along with theta. And let me do 2 pi here. And all this, you just have to play and practice. You could learn all kinds of different things here. But when I do this, these are called rose curves. They're like a rose, like a flower. And so you see what I got here is 8 of them. It doubled it. Okay? But look at this. So that was cosine of 4 pi. Now let me do cosine of 5 pi. You might think that there would be 10, right? It would double it, but let's look and see. Now there's only 5. I wonder why. Okay? Here is the reason is that when I had 4 here, let me go. When I had 4 and I did this, as it goes through and it comes back here, it's off center and it keeps doing it. So the other one, when I had 5, it actually traced through it twice. Okay? But this traces through it once, but the petals are off center, creating twice as many petals. But when it was 5, it traced through it twice, but it went over the same petals. So to show you this, let me do this. I'm going to go from just 0 to pi, okay, and I'm going to go back, and I'm going to do 5 here, and you'll still get the whole thing. Okay? And if I went from 0 to 2 pi, it actually traces over the same petals again. But now if I go back and I do 4 pi, you'll only get half of it. Do you see? It ended there, and then you need to keep going to get the other ones. So I need to go to 2 pi here. And then it would get all 8. So you can do some neat things there, and you could do the same with sine, and it just changes the orientation a little bit. Same idea. So there's 4 of them, and then if I do 5 here, and then that would be tracing them out twice. So really neat things, and there's just tons of interesting, cool things that you could do. So let me go back here, and maybe I'll change this to 10, and we'll do sine of 4 theta inside there. So they're nice and big, and then you get 8 of them. Now, what if I did another even one? If it's even, that's when you get double. So let me do 8 theta. Okay, so it's really neat. Now they're not as curved here. Do you see how they're straight edges? It's because of how it's evaluated. And so what I would need to do is I'd need to go back here and I'd need to make my step even smaller. So maybe instead of 0.13 I'll do 0.05 for my step, like that. And that'll make it smoother. It'll take it a little bit longer to graph, but now you can see that they're not flat. They're really not flat. It's just the way that it was evaluating, because it evaluates at those steps and then it connects those lines. And if it's not smooth enough, you don't get a very good picture. So for example, you can get some really weird things if I make my step 0.5, right? A really big step. Do you see that? Because it's doing it every 0.5 and it's connecting those. So it just doesn't look quite right, does it? Let me make my step 1. Okay, so that step really matters. So that step should be pretty good if you want pretty small if you want a nice smooth picture. Okay, so these are some neat things, and you can do things similar to this on Desmos, which is really fun, and it has some some neat capabilities. I'm not gonna do that. I would have to do a screen share or something. I'd have to go on Zoom. I don't think the software I'm using here can share the screen. But why don't you try Desmos out and see that you can actually do this kind of stuff. What I was going to say is I'm going to look for a video on YouTube that maybe has some other graphs that you can do. So you can do some neat pictures with these polar coordinates, and they would be things that you would not normally be able to do with regular functions, right? Because these are not functions at all. This is actually, r is a function of theta, but x is not a function of y, right? Let me show you one other thing here, if I can find the example with the parabola on its side and the hyperbola or whatever. The lines, the different ones. So here's a line. Let me just do a line. So here's that line, 3x minus 2y is equal to 5. It looks like this. So let's do that. And these lines can do weird things because there's some asymptotic behavior where it might not get the full line. So you really have to play around here. But okay, so I'm putting this in like that, but because you have these things all in the denominator, there's weird asymptotic behavior, so you have to be careful with your steps. So I'm going to do like a zoom standard, and then let's see what it does. So there it kind of got the whole, oops, sorry. Let me go back to my thing because I don't know if it was showing. So it looked like this, and there it got the whole line there. Okay, but let me change my step to, I don't know, 0.5. It might not get all of it. Oops, see, it kind of stopped up there. Okay, and so you just got to be aware of that. So if I go, let's do 0 to pi and see what happens. See, I didn't get all of the line. Now if I change my step to 0.1, there I got all the line. So the difference there was not the 0 to pi, but it was my step, right? With 0.5, you don't get the full line, but you do get more of it if I do 0 to 2 pi. So it's interesting how these things are working itself out. Let me do the one that was a parabola on its side, which you don't normally get to see because it's not a function, right? Here, this ends up being like a parabola on its side. So let me plug this in. So 2 cosine theta divided by sine theta squared. And then there you get to see the parabola on its side. But look at this. It's really weird how it does this, because it's actually tracing it out, I think, a couple times. And it's hitting it, evaluating it at different spots, and then connecting those dots. So instead of going from 0 to 2 pi, I think I only need to go from 0 to pi. And I won't see, now I don't get that. But it's also not very straight. And so now let me shrink my step down to 0.1. And now I get a pretty good parabola on its side. So you have to be aware of those things. You got the length of the interval for theta. You got the step that matters, and then your overall window too, of course, to get a good picture of things. So neat stuff. This is graphing using polar coordinates. So enjoy, have fun with that, play around with it, and I think you will enjoy it.